Hi everyone. What I'm going to show you in this tutorial video is a small tool that I made to generate input files that can be used with UserCalc and PyUserCalc. If what you have to start is mineral modes with depth and degrees of melting. Since the models in the PyUserCalc package rely on bulk rock partition coefficients to calculate trace elements and uranium series disequilibria during partial melting, you'll need a way to convert from mineral modes to bulk partition coefficients with depth. And so this is just a little calculation tool that does it for you, given a few input parameters. So you'll need a file, a CSV file that looks something like the one shown here, with columns for pressure in kilobars, degrees of melting as decimal percents, and mineral modes as decimal percents, all with depth. And to whatever final depth you want, these can go all the way to 0, or they can stop a little deeper if you're simulating a lithosphere that truncates your melting column. And then you'll also need to feed the model the input file generator tool mineral melt partition coefficients, which will be in tables that look like this. For all the elements you're interested in, if you want to do uranium series calculations with PyUserCalc, you will need these 4, but you also can include other trace elements for stable trace element calculations using the stable calc method, and you'll need all of the minerals with the same abbreviations that appear in your depth file with modes. It is also possible to have 2 different partition coefficient tables that have garnet or no garnet for use when you're calculating peridotite melting, so you can use a different set of deep and shallow partition coefficients. So I've done something like that here, and I'll follow up on some of these weird looking cells as I show you the code. So the new tool that you need to do this is the bulk_ds input generator tool. At the moment, the most recent version is the first one, so version 1, and all of the files I just showed you can be in your data folder. If you then run this Jupyter notebook, it looks something like this. It has a brief introduction explaining what the tool does, and then you can load your libraries. And then the first thing that you have is actually a template data table that illustrates what your input file should look like. I've just shown you one of those. This is a very brief one without very many layers, from just 10 to 5 kilobars, with a few minerals in it and some very simple numbers that don't change because this is just a formatting example. So I've loaded the one here that I just showed you. So I can bring that in or import it, and then see all of my data set here. It's abbreviated, but at least I can verify it's the correct one. Now, to do this, first I'll need to provide the tool with the list of minerals, which it can extract from this table, and the list of elements I want to run. So the first cell here extracts and lists those minerals. I can verify they look correct. And then I've loaded the elements that I'm interested in, and all of those elements are included in my partition coefficient table. There's a brief explanation here of what's going to happen with loading those data tables, as well as, again, a brief template showing what the table should look like. There is also some additional explanation here of what these weird cells are doing for garnet, which were imported straight from here. This is actually a little snippet of code that you could insert in the cells in your data table, and then those are imported and parsed as commands in the Python script. What this one will do is implement a formula where the partition coefficient for uranium in garnet is equal to 0.204 plus 0.01956 times the pressure, if the pressure is less than or equal to 30 kilobars. Otherwise, it will have a fixed value of 0.038. And there's a similar formula for thorium in garnet. These are the Landwehr formulas from 2001. Just as included here as examples. So it is possible to be more sophisticated like this for your partition coefficients than just putting in constant numbers for each mineral. However, these details are often not known or constrained, and so most of the time the expectation is you'll be putting in constant values. This tool is just set up so that it is possible to be a little more sophisticated. So here I'm loading both of those files, a spinel peridotite one and then the garnet peridotite one that includes formulas. So that's this file here. And the script is currently written so that it will apply the spinel peridotite case when garnet is not present, and the garnet peridotite case when garnet is present in the modes. It is possible that this could be added to in the future with some additional capabilities. This was just a relatively straightforward way to set it up for now. So you can load and verify both tables. It is possible to load the same table twice as both dfile1, oh here we are, dfile1 and dfile2, if you don't actually care about depth dependence of your partition coefficients. That also is perfectly valid. So if the second file was the same as the first, it simply won't display again. Now we're going to verify that the input tables that you have loaded match the lists of elements and minerals that are expected, and will spit out a warning if your input file was, for example, missing an element or a mineral that will be needed to determine your input file for PyUserCalc. So for example, if you left out uranium, but uranium was in your element list above, up here, the code would tell you that you're missing some information and you need to go back and edit your partition coefficient input file, and then you can run through these cells and load it again, and it should overwrite, replace the old version, and this should all look correct. Mine look correct, so I can keep going. I'm then going to make sure that the order of elements and of minerals matches my my list above so that I don't make any mistakes calculating bulk partition coefficients. If they're in a different order, this cell will simply rearrange them to match. And then I'm going to assemble a data frame that is currently empty of values for the bulk partition coefficients because I'm going to replace them. Now, this cell will actually calculate the bulk partition coefficients and replace them. And while it's not the best practice to calculate and replace cells within a data frame because it's slightly slower than other methods that can be used, these data frames and tables, computationally speaking, are very small, and this is a very computationally simple calculation. It is simple matrix multiplication, so it is so fast it makes no difference. So here are my bulk partition coefficients. I can verify that they look right. I also, if the cells Du, D-thorium, D-protactinium, and D-radium are present, there is a cell to automatically add a KR column. This is the reference permeability column for using UserCalc to calculate uranium series isotopes. At the moment, this is inserted as a simple column with all 1 values, or values of 1, as you can see here. Generally, if you're going to be changing your permeabilities, you'll probably be doing that non-linearly, and so you might want to wait till after generating this template file and then manually go into your CSV and edit it afterwards. You can also view your inputs for your various lithologies using the data inputs that go into the U series and stable element calculation tools for UserCalc. The top one is the uranium series plot that will include the KR, and the second has the partition coefficients for all the different elements that have been imported. Now you can give your input file, which will go into your data folder, a unique name that has something identifiable about it. You also can insert a comment, so you can modify all of this text within quotes, as well as the file name, just leave the quotes, and you can make them say whatever you like. This comment is simply for bookkeeping, so that if you need to figure out what your different input files are doing, you can tell them apart by opening them and reading the more detailed comment. And then this final cell will generate your CSV file and place it in the data folder. And that's it. Happy calculations.